Welcome everyone. So this is our 70th live stream geometry. We have me and 4 other people here with us. And today I'm going to go over the VMEO. So it's the Vietnamese Mathematical E-Olympiad. So it's a competition on the internet, and there's some forum called the Vietnamese Mathematical Forum. I haven't checked it out too much, but I took problems from that competition in 2015 and 2006. So that's what I'm going to do today. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. It's going to be in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. All right, so with that, I'm going to get started. Let me share my screen. So, sorry. So here's the first problem I chose. So we have a triangle ABC inscribed in a circle O. And P is a point on arc BC, so that AP is this median. So probably the easiest way to draw that is to draw the tangents at B and C to this circle and let them meet at a point, let's say D. Okay. So draw these two tangents. And then, so yeah, basically we know that ABPC is a harmonic quadrilateral. So let's do this. This is going to be point P, and ABPC is harmonic. E and F are the reflections of P over CA and CB. So that should be E, and that should be F. I'm going to rename them. And then K is the reflection of A over EF. So I've seen a few problems like this where you do like double reflections or triple reflections. So K is that point. And all right, let's see if it works this time. So Arabian Maths just try to join. Let's see if it lets him in. And then we take the perpendicular from K onto the line through A parallel to BC. So I'm going to draw that. And draw the perpendicular from K onto that. And whoops. We call that L. And we want to show that PA is equal to PL. All right, so I'm going to draw a few more segments just to highlight the symmetry here. So AFP, basically A is the circumcenter of FPE. And then I'm going to hide stuff I don't need. I might even be able to hide the tangents, but I'll keep them there for now. I think yeah, Arabian Math is still trying to join. I don't know what the issue is. Okay, so I think this is good. So yeah, A is the circumcenter of FPE because AF equals AP equals AE. And K is the reflection. So I don't know if it's worth drawing that circle. And K is what you get when you reflect A over FE. Okay, so we want to show that PA is equal to PL. Wonder if there's like another way to say that. So AFKE is a rhombus, right?
Looks like AK is the median.
AK is the median of
ABC.
Of ABC. Interesting. Let's see. So I'm going to draw the midpoint of BC. Yeah, that's an interesting observation. Yeah, and I can see why people like, yeah, like that's one thing that's like easier to see using GeoGebra, obviously, but yeah, I just like that the diagram's nicer, like than if we do it by hand. Kind of like that. Okay, so that's an interesting observation. So it looks like AK is the median of ABC. So let's draw the midpoint of EF. So we know AH and K are collinear because AFKE is a rhombus. How do we show that that's actually the median? There's a lot of interesting things here.
It looks like an angle trace. I'm not exactly sure about the details. It doesn't look hard to prove.
Okay.
Yeah, I think it's because of the parallel properties of isogonal conjugates, isn't it?
Oh, really? Isogonal conjugate?
Yeah, like if you have two isogonal conjugate pairs P and Q, and if you draw their parallel triangles, then like if you say P and Q are isogonal conjugates, then if you draw the parallel triangle, say of P, so DEF is the parallel triangle of P, then AQ is perpendicular to EF. Using that fact, I think we'll be able to show that AG and the median, AK is the median of triangle ABC.
Okay. So what are the 2 points that are isogonal conjugates? So P, okay, we want to show AP and AH are isogonal, right? Did you say that P and H are isogonal conjugates, or?
I think he meant isogonal lines instead.
Isogonal lines, okay.
Yeah, isogonal lines, yeah.
Okay. So we want to show that these lines are isogonal. And was your idea to use the isogonal line lemma or some other way? Okay. Yes, so P is an arbitrary point. Okay. So, okay, so are you, yeah. Then AQ is perpendicular to EF. Okay. So let's think about this. I think it's because you're taking ratios. So let's draw the midpoints of PF and PE. Then basically the, okay, I think you called it. So basically PI over PJ. Okay, yeah, so IJ is parallel to EF. Okay, so if A, I think I see what you're saying. So IJ is parallel to EF. And because of that, the perpendicular to EF from A has to be isogonal to AP. I think because but wait, where did we use that AP was the symmedian? We have to use that somewhere, right?
I think I've solved the problem.
Really? Okay.
Yeah, but first we need to prove that those are isogonal.
Okay.
So I'll just briefly explain my solution and then we will write it.
Okay.
So consider that point H that you marked on the picture. Okay, so we will need, okay, those are already marked. So I and J are the perpendiculars from P onto those sides, that is clear. So if we take a perpendicular from P to BC,
Okay.
by Simpson line, those three would be collinear.
Okay, using the Simpson line. Interesting.
And then we do the homotopy at P with ratio 2.
Okay.
So obviously that homotopy sends N to the intersection of EF and PN. And actually that point will indeed be the point H.
Okay.
I think there is some lemma. I think maybe the HM point. I think the H will be the HM point. Like that is some theorem. So that so then we will know that like that reflection of P with respect to BC would lie on the median.
Okay.
So I think that is something that we can prove, that H is indeed the desired point. So we will then have that H is the midpoint of AK.
Okay. So yeah, so then we could show that H is the midpoint of AK.
That is pretty obvious, since K is the reflection of A.
Yeah.
Line EF. And then because the angle ALK is 90 degrees, we have that HL equals HA equals HK.
And so then that solves it.
Yeah.
Yeah, yeah. Once we know that AH equals HK, then we're, or I guess it depends how we define H, but
yeah. But once we prove that the concurrency happens, like the midpoint and those, I mean, the altitude and those two lines concur, then we're practically done.
I wonder, do we even need to know that AK is a median?
I think we need, because I think I used that fact like in my proof, because it is, let's say, well known that the reflection of P in BC lies on the median, but we would need to prove that AK is indeed the median to like prove that H lies on AK.
Okay. All right. So, okay. So All right, that makes sense to me. It's well known that the reflection of P over BC lies on the median. All right. So let's think about this. Okay, so I'm going to read what Agaman wrote. Since AK is isogonal to AP, and AP is the median, which means that AK. So I kind of get, so I get that IJ is parallel to EF, and I'm just trying to think, is it because since AIPJ is cyclic, like what would we get if we reflected IJ across the angle bisector of ABC? Let's see, let me try that. I think Arabian Math, I think he has, let's see. So if we take one of these, for example, we reflect it across this. I'm going to hide this circle for now. It just takes up more space than necessary. So okay. So I think Arabian Math has a proof. I'm just trying to understand it. So we want to show AP and AH are isogonal. And we know IJ is parallel to EF. Yeah, I'm still trying to figure out. I think because AIPJ is cyclic, and like IJ is a diagonal of it, then I think what Arabian Math is saying is that a perpendicular to a diagonal of this cyclic quadrilateral, it's probably an easy angle chase, has to be isogonal. Yeah, it is an easy angle chase. Okay, so I'm going to write this out. So first of all, let I be the midpoint of PF. Let I and J be the midpoints of PF and PE. All right. And then basically AIPJ is cyclic because angle, since angle AIP is angle AJP is 90, that means that AIPJ is cyclic. And so yeah, actually we really don't need point D, but I'm just going to leave it there. So basically we have that angle J. Okay, so first of all, AFKE is a rhombus. So AF equals AP equals AE. That means that AFKE is a rhombus. And let H be the midpoint of EF. Okay. And so basically, angle, yeah, I think we can just use angle chasing. So we know AH is perpendicular to EF, and EF is parallel to IJ. So AH is perpendicular to IJ. So basically, we can, from there, I think we can use angle chasing. Yeah, so so we have EF is parallel to IJ, which means that AH is perpendicular to IJ. And so that means that angle JAH is 90 minus AJI. So angle JAH is 90 minus angle AJI, which is 90 minus angle API, which is angle PAI. So that's how we know they're isogonal. So AP and AH are isogonal with respect to angle BAC. So AH is a median. Actually, let me just replace it. Yeah, so yeah, I'll just say AH is a median. All right. Since AP is the symmedian. And then from there, the reflection of P over BC lies on the A median. So I'll say is the A median. And then I'll use the well-known fact Stefan said. The reflection of P over BC lies on the A median. That's well known. All right. So basically, so pH is so by a homophily at P, P with ratio 2, P and H are reflections across BC. And then it's kind of obvious at that point because it's by symmetry. So AH equals AK equals AL, or HA equals HK equals AL. So by symmetry, so since pH is perpendicular to BC, then by symmetry, PA equals PL. Yeah, that's a nice solution. And I like that we use this special well-known fact that if you reflect P over BC, it's the Humpty point.
Also, I want to add just another thing about this. I just saw that also the orthocenter of ABC lies on the line EF.
Oh, that's interesting.
That is kind of obvious after we know that H is indeed the HM point, or in other words, the Humpty point. I think it's called like that.
Okay, yeah, because the perpendicular H, yeah, the Humpty point, because yeah, if H is the perpendicular from the orthocenter to the median, then yeah, it's like you said, the orthocenter would have to lie on EF.
That really looks like something that is a kind of good configuration.
Yeah, looks like it's probably useful in other problems. I agree. All right, so I will move on to this one. So we have a triangle ABC. P is a point. I wonder if we've done this one before. Let's see. P is on the angle bisector. And then we draw PB and PC. This looks really familiar, actually. Let's see how quickly we can solve it. This is P. And we see where it cuts CA and CB. Yeah, Vietnam has a lot of good problems. Okay, so this should be E and F. And then we let EF meet the circle at 2 points. Actually, I'm not so sure if I've done this before. So M and N. A line perpendicular to PM, whoops. This should be N. Okay, so we draw the perpendiculars to PM and PN at M and N. And they intersect the circle at S and T. Okay. And then we want to show that ST is parallel to BC. That's interesting. Let me hide some stuff. But yeah, we haven't done this one on the channel before. Well, you know what, I'll leave this just for a second. Just gonna hide the angle bisector now. Let me draw everything back in. All right. So we have someone new who just joined from Greece. I think he just joined us right now. So welcome to the session, Constantinitis. Sorry if I mispronounced it. Yeah, thanks for joining us. So let me draw in a couple extra segments here. And I think that's everything, right? Oh, I have to draw EF, I have to draw this. So yeah, this is an interesting configuration. I've never seen this kind of idea before. Interesting. So yeah, this right angle makes me think we're going to use cyclic quads somehow. Now, this is a very nice problem.
Intersect MS and NT.
All right. MS and NT.
MS and NT.
Okay.
So it goes a bit away from the picture in this case.
Yeah, let me adjust the diagram a little bit. I don't know if it's easier if it's an acute triangle or a let's see. Oh, it looks like it might be easier. Maybe if it's like a very narrow triangle, that would make it easier. Let's see. How about this? Let's see where these intersect. Yeah, it's still too far away. What if?
Just scale the triangle a bit down.
Yeah. Yeah, and I think if I tilt it a little bit, well, no, that doesn't do that much. But yeah, I think that should be good.
All right, so I should say what I wanted with this point. This problem is equivalent to showing that GP is perpendicular to BC.
Interesting.
So a bit why that is indeed true is because if intersect the circumcircles, so intersect the circumcircles of MPS and MPT.
Okay. At this point?
Mm-hmm. Yeah, so that yeah, so proving that ST is parallel to BC should be equivalent to proving that S. Actually, we know that SH and T are collinear.
Yeah. So it's the same as showing that GP. So yeah, I guess first we show that GP and H are collinear, right?
That is by radical axis theorem.
Okay. By the radical axis theorem, G. Oh yeah, you're right. Yeah, because SMNT is cyclic. Interesting.
Now I see that the point G may or may not be useful here, but yeah, because I missed that H is already collinear, but it's okay in the picture nevertheless.
Okay. So Arabian math said PE and PF might be isogonal. Let's check, see if that's true. Sorry. So at angle FPE or FPM and NPE. They're not quite isogonal. It's close, but all right. Okay, so yeah, that gives us a lot of information. I feel like yeah, we have to use somewhere that P lies on the angle bisector. Yeah, I like adding that point. I don't know if it's worth drawing the midpoint of arc BC and then using that P passes through that.
Draw it. It doesn't look like a bad idea.
Okay. There's the midpoint of arc BC. Call it I. Looks like Constantinides got disconnected. Are A, B, and I collinear? They should be. Yeah. I don't know why it didn't look like it for a second. Okay. All right. So, yeah, how do we use that P lies on angle bisector? Are there some other cyclic quadrilaterals? Is maybe AFPN is cyclic? No, I don't think so.
We have that GMPN is cyclic.
GMPN. Because it has two right angles. So yeah, triangle BIC is isosceles. So yeah, basically, if we want to show that, we want to show GP is perpendicular to BC. So I guess another way to say that H is the intersection of these two circles, PMS, the intersection of the circles PMS and PNP. Okay, so yeah, we want to show that GP is perpendicular. Yeah, we haven't used yet that M and N lie on EF. Okay, yeah, so M and N. So I wonder when I move P, is the line MN always remain parallel to itself, like as I move P?
No.
No, it doesn't. Okay. Do PM and PN move in a fixed direction? It almost looks like is PM always parallel to itself as they should? What if PN is anti-parallel to ST? But the thing is, when I move P, point G also moves. So I wonder if that changes things. So like, but wait, yeah, does angle GHT? Yeah, because this angle can get thinner and wider. Yeah, I think if G stayed in the same place, then that would be true, because PN is always anti-parallel to ST, but because G is like moving as I move P, I'm not sure if that's true.
Intersect PM and PN with the circumcircle.
Okay. So that would give us some diameters, right?
It looks like this line is also parallel.
That's interesting. Okay. Well, because KT is a diameter and SJ is a diameter, so that would be a rectangle. So yeah, that kind of makes sense, right?
Oh yeah, but that may simplify our problem, since we really need to show that only one of them is parallel and the other will follow.
Yeah.
So this other one may be easier to show.
Yes. So K. Yeah, because then we don't need to draw perpendicular. Yeah, then we could just show KJ as. So really, we could remove ST. Yeah, we could just hide it. And just show that PJ. Yeah, actually, and then we wouldn't even need these circles, right? Yeah, we just need to show that JK is parallel to BC. That might simplify things. So let me, we can always add this back later, but I think that might be the best way to go. Because yeah, that seems like a simpler way to state the problem, right? We can make it a little bit wider of a triangle. And I can hide this. No. No, in general, Chevians. What do you mean no IG or no in general? Oh, I guess. I was thinking in general. All right. It's kind of a nice picture. Yeah, so we want to use this angle bisector right here. Pascal's. Yeah, that's an interesting idea. Can we use Pascal's theorem somehow to show that they're parallel? I feel like there's probably one more cyclic quadrilateral that we have to find. So yeah, how do we use that P lies on the bisector? It almost looks like, no, I don't think BF, yeah, there's no way BFEC is cyclic. But yeah, showing that KJ is parallel to BC seems simpler. Yeah, is there a way we can use Pascal's? So yeah, it feels like it should be possible. So basically, we want to show that AB and AC are isogonal in angle KAJ. Maybe we could use the isogonal line lemma. So it's another way to say that is AF and AE are isogonal. What if PF intersects AB at R and the same for BP? Let's try that. So we'll call it R and S. Yeah, and now maybe that would make Pascal's easier somehow. I don't think A is the midpoint of RS or center of that arc, but it's worth checking. Yeah. Maybe RS, MN, and KJ concur. See, RS, no, I don't think so. One second, guys, I'll be right back. All right, let's see. Thanks for waiting. Is the line joining, actually, sorry, let me first change this from S, and I'm going to read that comment. Oops, I didn't want to make a line, I just wanted to rename that. Is the line joining PK intersect AB and PJ intersect AC? It almost looks like it's parallel. Let's see. Yeah, maybe it is. I think it's just barely not parallel, actually, because if you go far enough, let's see. Yeah, like you could see they intersect like all the way over here. So yeah, I don't think so, but it's an interesting idea. Square root of BC inversion could be. Yeah, let me think about that. So we do a square root of BC inversion at A. So it'd take B to C, C to B, and then P would stay on it. I'm not that good at square root of BC inversion, but if you can figure out a way to make it work, yeah, feel free to put in the chat. Is RFEU cyclic? No. So yeah, what happens if we try to use Pascal's? So MJ intersects NK at P. Do we have any other points like that? You have P, F, and E. So RAU, BC. What if we did RAU, BCI, and we try to use Pascal's? Something like that. MN and the A external bisector and BC are concurrent. Interesting. So yeah, they must concur pretty far away. Let's see. That's interesting information. So basically, if I add this stuff in, yeah, that's good to know because that allows us to use the fact that P lies on the angle bisector. Yeah, because then these are like a harmonic bundle. Yeah, that's just straight projective GEO. It's a good observation. Yeah, I think, yeah, that's worth keeping in the diagram, I feel like. Yeah. All right, so we have Khan joining us. Thanks for joining, Khan. So I think this is our second problem. So we're doing the Vietnam Math E-Olympiad. So it's like an internet competition. And yeah, so basically I hid some of the stuff in the problem originally. If we could show JK is parallel to BC, that would solve the problem. So I kind of...
I think BN and CM, these two lines, they will intersect at a point on the A bisector, I guess.
Okay.
Can you pull up the diagram a little bit? I cannot see the point beneath it. Oh, yeah, it's point I.
Oh, sure. 1 second.
Yeah, okay, thank you.
You're welcome. So basically, this problem has 2 points S and T in it. And we found that if we prove that JK is parallel to BC, it's the same as showing that ST is parallel to BC. So we got rid of S and T. But previously, they were these points right here. So yeah. So showing that ST is parallel to BC, it's the same as showing that JK is parallel to BC. All right. Oh, sorry. Let me read what. So Arabian math. You were. What were the two things you said we should try to intersect? Was it BN and CM? Or was it you Arabian math? Sorry. Ah, okay. Yeah, we just have to use Pascal on the right thing. So maybe MKB NJC. So what if I draw the parallel through P BC? Does that pass through any important point? It's hard to see anything. Yeah. I'm going to delete this.
I think there are 2 points which are useful to add.
Okay.
So intersect MP and NP with BC.
MP and NP with BC. Okay. And then I'm going to read what Constantine wrote. A second. All right. Let me see if I can do this. Yeah, I'm gonna hide S and T for now, just to make my life easier. Oops, I just wanted to hide that segment. Okay, so I'm gonna add this point right here. So it's point Q.
Now I want to say why I added these points. So it is equivalent to show that the whole problem is equivalent to showing that MNOQ is cyclic.
MNOQ is cyclic. Okay.
And that looks approachable by power of a point from L, with maybe some projection of points and stuff.
Okay.
Also, another thing that I just found is that QM and NO, those two lines, they concur at the midpoint of the
Arc BAC.
Yeah.
That's really interesting. So yeah, that would probably be really helpful if we showed that. All right, let me see, what did constant, so before I get to this, I just want to read what he said. So he's saying the line through P parallel to BC is tangent to PMN. I think if that's true, are MNOQ cyclic? Stefan was just saying that if they were cyclic, that would solve the problem. All right. And yeah, I think what you said, Constantinitis is true. I think that would follow from an angle chase.
I think that that parallel is tangent is equivalent to the problem.
Is equivalent to the problem. Yeah. All right. This follows from Ricard. So MNOQ are cyclic. That follows by Ricard's theorem. Constantinitis. So wait, how does it, or what, are you saying the fact that this is cyclic comes from Ricard's theorem? Yeah, it's really interesting that QM and V are collinear. VAOQ is cyclic then. That's interesting. Okay, so KCJB that cross ratio is equal to NRMU. Oh, by projecting through P. Interesting. All right, I think we're pretty close here. To figure out a couple more things. Yeah, I guess we want to use the fact that angle DAL, so I should draw this. This angle QVO 90 degrees. Well, that would mean MVN would be 90, so I don't think so. But yeah, that's interesting that Q, so NP intersects it at Q, and then, yeah, that seems like it shouldn't have that hard a proof. So wait, so M and N are where EF meets the circle, and then NP cuts BC at Q, and we want to show Q, M, and V are collinear. Okay, so we know, so yeah, VA and L are collinear. Yeah, there's a lot of stuff we know here. So really, you could start by taking triangle ABC, and then you draw VAL. And then you kind of pick another line through L, and it cuts the circle at M and N. Interesting. Is QMAL cyclic? Yes. Interesting. Not sure if that's obvious or not. So yeah, Stefan was thinking of like using power of a point, maybe. Yeah, there's a lot in this configuration. It's a good one. Yeah, and I think it would be an angle chase to show that QMAL is cyclic. Like once we know that QM and V are collinear.
I think it is the Michael point.
Michael point?
Yeah, Michael point theorem. Since A will be the Michael point of M and OQ.
MnOQ. Oh, I see. Yeah. So yeah, ANOL is going to be cyclic. Yeah, it's all, I mean, yeah, the Meckel configuration in general is just pretty rich. Okay. Now we just need to find one more thing here. So yeah, is it obvious that Q and V are collinear? So we really don't know that yet. I don't know if it's better to define it that way. Yeah, like another way we could do it is like, if we define M prime to be the intersection of V, Q in the circle, can we show that M prime, E, and F are collinear? Well, yeah, I feel like it's, okay, so as we move P, point L will stay in the same place. We know that. Yeah, is it clear that V, M, and Q are collinear?
I doubt. I think it is the sufficient what we need to prove.
Oh, if we could show that V, M, and Q are collinear, it would.
Sorry, can I speak for a while, Michael? I think I have the idea. So I think Stefan said that if we can prove the tangent from P of circle PMN is parallel to BC, then this is equivalent to the problem, right?
Yeah, yes.
Is it right, Stefan?
Is it what?
Yeah, I think it is sufficient because when we take a look at the original statement with the perpendiculars, and the thing I talked earlier about the perpendicular, when we added that point G at the top and then the perpendicular thing. I don't know if you're there.
Yeah, I can prove it. I can prove it. Okay, so I think I will start doing it. If you guys don't mind. So can you draw the tangent from A of circle ABC?
The tangent at A?
Yeah.
Okay.
And let it intersect EF.
Okay.
So by applying Pascal theorem on 5 points A, U, R, I think by applying Pascal, we can prove that U, R, and W are collinear.
Okay.
And, next, I will prove that WP is parallel to BC.
Interesting. Okay.
Okay, so can you label the midpoint of BC?
Yeah. So for your proof, do you need points Q and O?
Oh no, you can delete them just for easier observation.
Okay. Yeah, it'll be interesting. Yeah, it would be interesting to see if there's a proof using that. But yeah, we don't need it for now. Do you need point L?
Point L. Oh yes, I do.
Okay.
Let's call the midpoint of BC. So the idea is I will prove that PW is parallel to BC using harmonics. So I will be using this midpoint.
Okay.
Can you project? Like let PO meets EF at a point.
Okay.
And let it meet AL at another point.
Okay.
I think the point here isn't right. I think.
Yeah, I think I have to hide. Yeah, before I create the point. Okay. So, and what was the other thing you wanted me to AL?
AL, yeah.
Okay.
Okay, so we have OQPV is a harmonic because of it's like the concurrence of the three lines AD, FC, like consider the complete quadrilateral EF, BC, LA. We have BE, FC intersect at P, so it must be harmonic.
Okay. So basically, so you're saying OPQV is harmonic because yeah, like if you project it onto this point, then that would mean A, that point, P and D are harmonic.
Yeah,
And that's true. Yeah, and that's true because A, D, C, F, and B concur. Okay, that makes sense.
Because they are harmonic and AP is perpendicular to AV, so we must have AP is the angle bisector of AO of OAQ. So in other words, AO and AQ are isogonal in angle BAC.
Okay, yeah, so AO and AQ are isogonal.
So AQ must be the median line. And however, we have AW is the tangent. So about the tangent and median harmonic conjugation, we have FEQW is harmonic.
Okay.
So when you project from P, you will have PB, PC, PO, and PW is harmonic. So PW must be parallel to BC.
Ah, that's really nice. Okay.
So since we have PW is parallel to BC, I think it's easy to show that PW is the tangent by applying the like an angle chase, I think, just an angle chase.
Okay, that's really nice. I love this proof. It used a lot of harmonic and it used Constantinides' idea to show the tangency, and then
like this is just like a lemma. If you like connect any point from BC, in this case it is point O, and you take PO intersect EF at a point Q, then you will always have AO and AQ are orthogonal.
interesting.
Yeah,
that's really cool.
Yeah.
All right, so I'm going to make some room for the proof. Let's see. Let me shrink the diagram a little bit just so I can have some room to type it up. All right. So All right. Let me unhide points S. T is really hard to see. Okay. Okay, so PMS is a right angle and PMT is a right angle. So yeah, it's hard to get this all in one diagram, but I'll find a way to do it. So okay. Oh, Luis Gonzalez had a handout. I'll have to check it out. Okay, there's so much stuff we added here, but so let MP and NP meet the circle at J and K. So then, so SJ and PK are diameters. And that implies that SKJT is a rectangle. And that means that ST is parallel to JK. Fix that number sign. Okay, so that's how we start out. Okay, so so then we use stuff about harmonics. So so I'll say let AP meet BC at point D. So let O be the midpoint of BC. Let AP meet BC at D. And then we know that BCD, and so let EF meet BC at L. B, C, D, and L are in harmonic conjugation. And that implies angle DAL is 90. Since angle BAD equals angle CAD. And then we let EF intersect RU at W. Actually, did we use R and U for this, or we just drew the tangent at A? I think we just drew the tangent at A, right? But then we showed that R, U, and W are collinear. So, sorry, I see the chat. Okay. Oh, there's an online math club? I didn't know about that. Okay. let the tangent to O at A meet EF at W. All right. And let's see. So first we showed, okay, so A, Z, P, and D are in harmonic conjugation. So that means that, okay, so A, P, Z, D. And that means that V, Q, P, O are in harmonic conjugation. For V, P, Q, O are in harmonic conjugation. There we go. And then we can project through P, or wait a sec. Sorry, what do we do after that? I'm trying to remember. Oh, so we want to show AQ and AO are isogonal. Oh, because angle PAL is 90. Then that means that AQ and AO are isogonal. So AQ and AO are isogonal. Or I'll just say angle OAP equals angle QAP. QAP. Okay. And that means that AQ is a symmedian. AQ is the A symmedian. And then once we know that, by a well-known lemma, that would mean that F, E, Q, W are in harmonic conjugation. So AW is tangent. That's by a well-known lemma. And then once we know that, projecting through P, we would get that BC, so I don't know if I'm doing this in the right order, and then BC, and then the point at infinity are in harmonic conjugation, and that means that PW is parallel to BC. So FE, So it would really be CB. Yeah, I'll just swap this. Why not? Okay. Yeah. Or I'll say CBO and PW cap BC. That's probably the right way to write this. Okay. Sorry, and then by an angle chase, it's not hard to show from there that PW is so if we could show that PW is also parallel. Let me think how we want to do this. PW is also parallel to JK. Then so we know PW is parallel to BC. Is it obvious that PW is parallel to JK? I think it is because actually, yeah, what do you do after this point? Oh, because, so we want to show WP squared is WN times WM. Can we use harmonic conjugation for that? So yeah, do you know where to go after this point? Maybe I'm missing something obvious. So PW equals, oh, okay, so PW equals AW. So I'll just, yeah, so I'll say by an angle chase, PW equals AW. And that implies that WP squared or PW squared equals AW squared. And that is equal to WN times WM. And that means that WPN is WPN equals angle PMW equals angle JMN equals angle JKN, and that means that we have the ST. Okay, if WPN is JKN, then basically we have PW, if BC is parallel to PW is parallel to JK is parallel to ST. Okay, so a nice proof. So I'll move on to the next one. But yeah, I wonder if there's any ways to simplify this proof. But yeah, we ran out of space. I don't know if you guys can see that at the bottom. So I'll move on to the next one. We're about halfway through. Okay, so this one, just checking who's on. So we have an acute and obtuse triangle